Alright, an unexpected fifth video because the last video stopped when I did not want it to. So 31 through 35, but it did give me a chance to at least get my reference tables up on the computer. So 31. Should be an easier question, but sometimes people get really lost when they have to use the charts in the reference table for modern physics. Let's take a look at that very quickly. We're going to be looking at the chart on the left-hand side of page 3. Classification of matter. All matter can be broken down into leptons and hadrons, two different classes of matter. The leptons are all displayed right here. They cannot be broken down any farther. They are all fundamental. There's nothing inside of an electron that means that you can't split it apart. Hadrons, on the other hand, are all made up of quarks, different combinations of quarks. Depending on what combination they are, hadrons can be grouped into either baryons or mesons. We want the mesons. Baryons are made of 3 quarks. Mesons are made of a quark and an antiquark. Remember, antimatter is just regular matter that has the opposite sign. So an anti-up quark would have a sign of -2/3 E. We want a meson. We want to know what a meson could be composed of. A quark and an antiquark. Okay? This chart is not particularly hard to read once you get the hang of it. So, let's look through our different answers. Could a meson be made of a top quark and a bottom quark? Neither of those are antiquarks. We need one quark, one antiquark. That does not work. An electron and an anti-electron. Nope, that won't work either. Electrons are leptons. That does not work. Strange quark and an anti-charm quark, quark and antiquark, that works. Up quark and a muon, a quark and a lepton, you cannot combine those. The answer must be 3. In addition, please remember that any combination of particles must have a whole number charge. Top quark and bottom quark, you would not get a whole number charge. That cannot possibly be a combination. Electron and anti-electron. Remember what happens when matter meets its antimatter counterpart. It will annihilate. All that mass will just turn into energy, and energy does not, well, first of all, that would not be a meson. There would be no more particle there. It would just be energy. But that won't work either. Strange and anti-charm actually will turn out to give a whole number of charge, and up quark and a muon, that will not either. So 2 different reasons that this is the only possible combination that will give us a meson. Answer is number 3. Okay, let's look at question 32. Energy level question. An electron in an excited mercury atom is in energy level G. What is the minimum energy required to ionize this atom? So, we're actually on the same page. We go up to the energy level diagrams. We're going to look at the one for mercury. Right now, the electron in the mercury is in G, which means it has this much energy, -2.48 electron volts. We want the minimum energy required to ionize it. In other words, we need to take the electron that's in this energy level, kick it up at least to here. Ionization means that that particle will no longer be a part of that atom. It will be able to move and freely move throughout space. It will no longer be tied or bound to that atom. So what this really means is we need to give it some energy so it's no longer bound to that atom, to that nucleus. Right now, it's in an energy level state of -2.48 eV. It needs to get up to at least 0. It just needs to not be negative anymore. You can use an equation for this, but really I think this one actually turns out to be kind of common sense. Right now it has -2.48 EVs, needs to get up to 0. How much do we have to add to bring it up to here? +2.48 EV. Now, if you were going from one energy level to the next that does not include ionization, I would absolutely use the equation, maybe one of these, E photon equals EI minus EF, or depending on which way you're going, EF minus EI. But for this one, I don't think it really matters all that much. It should be fairly obvious. So the answer to this question is choice 3. The next question I think is kind of tricky because you have to. It takes a little while to get used to get into the question. The student is standing in an elevator that travels from the 1st floor to the 10th floor of a building. The student exerts the greatest force on the floor of the elevator when the elevator is doing what? When it's accelerating upward as it leaves the 1st floor, when it's slowing down as it approaches the 10th floor, when it's moving upward at constant speed or at rest on the first floor. So, student exerts the greatest force on the floor of the elevator. Let's think about what that means. What else must be greatest? If the student is pushing really hard on the floor of the elevator, Newton's third law says that the force of the elevator on the student must also be at its greatest. Force of elevator on student is also greatest. Greatest as well. And what is that force called? The force that the elevator puts on the student. It's the elevator floor pushing up on the student. We would call that the normal force. So when is the normal force going to be the biggest? Well, let's draw a little free body diagram for the student. It's usually easier to do the student, to draw the student in this case. There's only two forces acting on the student. There's the force of gravity, which points down. And there is the normal force, the force from the elevator, that points upward. Now, right now as I've drawn this, those two forces are about equal in length. They're balanced. What would that mean about the net force? It would mean there is no net force. And if there is no net force, that means the object is not accelerating. Okay? We want the greatest force from the floor on the student. So we want Fn to be really big. The force of gravity is not going to change. The way to make Fn really big, and therefore to make this force big, well, if we draw this bigger, we no longer have balanced forces. As a matter of fact, we now have a net force that points up, which means the acceleration must also be up. So what would happen in this case when the force of the student on the floor is really big, meaning the force of the elevator on the student, the floor of the elevator on the student is really big, we would have an upwards acceleration of the student. The force is going to be biggest at this point when the elevator is leaving the first floor. The normal force will be the same size as the gravitational force for 3 and 4, when it's moving at constant speed and when it's at rest. And the the normal force will actually be smaller than the gravitational force as the elevator slows down as it gets to the top. There's a lot of thinking that goes into this one. But the point is that the biggest force will of the student on the floor, which is the same time as the force of the floor on the student being biggest, is when the elevator is just starting to move upward, but it's accelerating upward, and that force is upward, meaning the normal force, the force from the floor on the student, and vice versa, is very, very big. A lot in that question. 34 is a little bit of a break, and 35 is not bad either. 34 is a straight up kinematics question, okay, fairly plug and chug. Bottom of a hill, car has an initial velocity of 16 meters per second, that is VI. The car is uniformly accelerated at negative 2.2 meters per second squared. Accelerated means that's the acceleration for 5 seconds, that's T, as it moves up the hill. How far does the car travel during this 5-second interval? We're looking for D. I was actually reading something recently that said kinematics is barely even physics, it's not really science, it's more math, and I understand where they're coming from with that. There's not a heck of a lot to, I wouldn't go that far, I should say. I understand where they're coming from, I wouldn't go that far. At some points, kinematics does get very equation-y, where you're just throwing numbers into equations and trying to get an answer. I know I try and explain almost as much kinematics as I can with the time that I'm allowed. It turns out there are some kinematics equations that I stay away from necessarily having people get an intuitive feel for or deriving, just because it takes a little bit too long. And the one that you need to solve, this question is one of them. But it's a very familiar equation from the beginning of the year. D equals VIT plus 1/2 AT squared. All we have to do is plug in to solve for D. And again, I'm not trying to say kinematics isn't useful. It certainly is. But they do have a point in that when you get an equation like this, it is possible to understand where this comes from. It's a little bit above the level that you need for a Regents class, in my opinion. So I finished plugging everything in. If I solve this, I should get an answer of 52.5 meters. Choice number 3. Last question. Particle enters the electric field between two oppositely charged parallel plates as represented in the diagram below. We have a particle moving this way between two parallel plates. Which particle will be deflected toward the positive plate as it enters the electric field? We need to remember something about what happens with different types of charges. Which one will go towards the positive plate? Probably a negative particle, because we know that opposites attract. We know that opposites attract. So this particle should be negative. Okay, and that would also make sense because then it would be repelling away from this negative plate. So, we look down here, we just got to figure out which one of these is negative. A photon. That's not really negative. It doesn't really have a charge, it's just light. Light does not have a charge. Can't be that. Protons, hopefully you know by this point, are positive. Electrons, hopefully you know by this point, are negative. Neutrino might throw you off for a second, but look at the beginning of that word. Neutrino sounds kind of like neutron or neutral. Going the wrong way. And we can see that all the neutrinos actually have zero charge. There are three different types of neutrinos. They're all neutral. Okay? Neutral particle would just go right through there. So the answer to this one is number 3. That does it for part A. I'll be back with part, I believe it's called B1.